B-trees are a type of self-balancing search tree designed to efficiently manage large amounts of sorted data, commonly used in databases, file systems, and other storage systems that require high-performance access. Unlike binary search trees, where each node has at most 2 children, B-trees are multi-way search trees in which a single node can contain multiple keys and have multiple children. This property allows B-trees to remain shallow even with a very large number of elements, which minimizes disk access, a critical factor in database and file system performance. The B-tree was first introduced by Rudolf Baer and Edward McCreight in 1972 to handle large-scale data stored on secondary storage devices, where reading a node from disk is significantly more costly than operations in memory. B-trees are particularly suitable for storage systems because their nodes can be sized to match the block size of the storage medium, ensuring that each node read or written corresponds to a single I/O operation. A B-tree of order M, sometimes called a degree M, is defined by several key properties. Each node can contain at most M1 keys and at least M2 keys, except for the root, which can have fewer. Every internal node has children equal to the number of keys plus 1. Maintaining a hierarchical structure that allows logarithmic search performance. All leaf nodes are at the same depth, which ensures that the tree is balanced and that the path from the root to any leaf has the same length. This uniform height property guarantees that operations such as search, insertion, and deletion can be performed in O log n time, where n is the number of keys in the tree. The ability to store multiple keys in a single node also reduces the height of the tree compared to binary search trees, which is especially advantageous when data is stored on disk, as fewer disk accesses are required to reach the target key. Search operations in B-trees follow a process similar to that of binary search trees but generalized for multiple keys per node. Starting from the root, the algorithm compares the target key with the keys in the current node to determine which child subtree to traverse next. Since the keys in a node are stored in sorted order, a binary search can be applied within the node itself for efficiency. The search proceeds recursively or iteratively down the tree until the key is found or a leaf node is reached, confirming that the key is absent. Because of the logarithmic height of the B-tree, searches are efficient even for very large datasets, which is why B-trees are widely used in database indexing. Insertion in B-trees is more complex than in simple binary search trees due to the requirement of maintaining node capacities and tree balance. The insertion process begins by performing a search to identify the leaf node where the new key should be inserted. If the node has fewer than M1 keys, the key is inserted in sorted order, and the operation completes. However, if the node is full, a split operation occurs. The node is divided into 2 nodes, and the median key is promoted to the parent node. This splitting process may propagate upwards if the parent node also becomes full, potentially reaching the root. If the root splits, a new root is created, and the tree height increases by 1. This splitting mechanism ensures that the B-tree remains balanced and that the number of keys per node adheres to the B-tree properties. Deletion in B-trees is similarly nuanced. The goal is to remove the target key while maintaining the minimum number of keys in each node and the balanced structure of the tree. If the key to be deleted is in a leaf node and the node still meets the minimum occupancy requirement after removal, the key is simply deleted. If deleting the key would cause the node to fall below the minimum number of keys, the tree performs borrowing or merging operations. Borrowing involves transferring a key from a sibling node with more than the minimum keys, while merging combines the underfull node with a sibling and moves a key down from the parent to Maintain tree properties. Deletions from internal nodes often require replacing the key with its in-order predecessor or successor, followed by deletion from the leaf node, ensuring that the tree structure remains consistent. These operations guarantee that the B-tree remains balanced and efficient after deletions. B-trees support several additional operations, including finding the minimum and maximum keys, counting nodes, determining tree height, and performing traversals such as in-order, pre-order, and level order. These operations take advantage of the multi-key node structure and balanced nature of B-trees to perform efficiently. For instance, finding the minimum key involves descending the leftmost child pointers from the root to a leaf, which is always O log n. Due to the tree's balanced height, level order traversal is particularly useful for database systems because it allows reading nodes in the order they appear on disk blocks, which reduces I/O operations. The advantages of B-trees over other data structures are numerous. Their height-balanced property ensures predictable operation times, while the multi-key node structure reduces tree height and disk access frequency. B-trees are scalable, handling millions of keys efficiently, and their operations are designed to maintain strict balance rules automatically. Variants such as B+ trees and B-trees further optimize B-tree operations for specific storage requirements. B+ trees, for example, store all actual data in leaf nodes while using internal nodes only for indexing, which improves sequential access performance, a feature highly valued in database systems. B-trees improve space utilization by redistributing keys during splits, reducing the frequency of node splitting. In conclusion, B-trees are a fundamental data structure in computer science, particularly for database indexing, file systems, and storage management. They maintain balance through well-defined insertion and deletion operations, ensuring logarithmic search, insertion, and deletion times. Their multi-key nodes reduce tree height and disk I/O, making them highly efficient for large datasets. By supporting additional operations like traversals, minimum, maximum retrieval, and counting nodes, B-trees provide a versatile and robust framework for managing ordered data. The careful combination of node splitting, merging, and borrowing ensures that the tree remains balanced and height efficient at all times, making B-trees one of the most important structures for persistent storage and high performance data access. Their variants, including B+ and B-trees, extend their applicability, highlighting the B-tree's adaptability and critical role in modern computing systems.